find f sub yx. Okay, so I took the derivative with respect to y, and now I'm taking the derivative with respect to x. Alright, so y was the variable, but now I'm switching modes, and x is now the variable. X is the variable. So x is the variable. Okay, so familiar, denominator times the derivative of the numerator. X is now the variable. So think about distributing the 4x through that. Well, actually, I don't even, you know what, in this, you don't even need to distribute it because you have x. Y is a constant right now. So 4 is a constant. 1 minus 1.6 y squared is a constant. So x to the first power is just being multiplied by both of those. Alright, so this is the derivative of 4 times 1 minus 1.6 y squared times x to the first power. All of this is just a big constant. So the derivative of a constant times x is that constant. Oh, wait a minute, sorry, x is now a variable. Okay, so denominator, derivative of the numerator, minus the numerator times the derivative of the denominator, where x is being treated as the variable, y is being treated like a constant. So the derivative of this is 0. The derivative of this is 1x to the first power. Okay, so they both have an e function, they both have the 4, they both have the 1 minus 1.6 y squared. I factored everything out of here. Over here, I am left with just x squared, right? And then in the bottom, we have what's been happening in every one of these problems. One of these factors out with that. Look at what we have on the board over here, and then look at f of xy over there. What do you notice? And we're watching Sesame Street. They're the same. They're the same. And guess what? If your function is continuous, that always happens. All right? If your function's continuous and differentiable, that always happens. And for the most part, we're going to deal with functions that are continuous and differentiable, all right? So I'm putting the caveat, if you have some kind of discontinuity, like some kind of vertical asymptote thing going on, or some gap, then, you know, no rules hold. But if your function's smooth and continuous, then that always holds. So the benefit of understanding that is, one, if you're interested in both rates of change, realize that they're going to be the same. Two, sometimes it's much cleaner to work with the one rather than the other. I mean, in this case, I think they were both about the same amount of work. but every once in a while, if you focus on first finding the derivative with respect to x, say, it cleans up right away, and then your derivative with respect to y is easy to find, compared to, you know, the other way around. So, again, some problems it's not going to matter who you pick first. Sometimes it'll make it cleaner to pick one first over the other. But again, for the most part, any functions we're going to deal with are going to be smooth and continuous. And so the order of the partials does not matter. And it's to the point where it doesn't matter even at higher order. So again, this is more of a theoretical idea than a practical idea. But, you know, let's say I took the derivative with respect to x, and then I took the derivative with respect to y, and then I took the derivative with respect to x again, and then I took the derivative with respect to x again. That is going to be the same as if I just first focused all on x and then focused on y. The order doesn't matter. And you could have more than two input variables. So I could have a function where I'm plugging in x, I'm plugging in y, I'm plugging in z, I'm plugging in w. So I have 4-dimensional input, and my output's the 5th dimension. You could have something like that. You wouldn't be able to graph it, but you could have something like that. And for those kinds of functions, I might take the derivative with respect to x, and then y, and then z, and then x again. That would be the same as if I took the derivative with respect to x twice, and then y, and then z. Or if I started with z, and then y, and then x, and then x. The order doesn't matter. 4 functions that are continuous and differentiable.
Wait, so what's an example of a 4-dimensional whatever?
Well, I mean, you could make up any kind of